Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to the A-Level Cookbook. Today I'm going to be doing the OCR A-Level Chemistry A 2022 paper. So if you look at this first one then, it says, which statement is correct about the different rates of hydrolysis for RCl and RBr? So what that means is we're breaking RCl and RBr. Now, the only difference between these two is that they're both halogens. The only thing that's different is that one is lower down in the group. The only difference between these two is literally just that it's Cl versus Br. So let's have a look. RBr is hydrolyzed faster because Cl is more electronegative than Br. That doesn't explain why. Although that is true, that is more electronegative. It's not telling us about that. Doesn't explain directly how the rates of hydrolysis are different. So RBr, so that one's out. It's not telling us the direct thing. If we're talking about different rates of hydrolysis, it's got to do with the bond strength that matters, not the fact that they're electronegative or not. It's how strong the bond is that ultimately determines that. So RBr is hydrolyzed faster because the CCl bond enthalpy is greater. So the bond enthalpy by definition, well, rough definition is, it's the mean enthalpy change required to break 1 mole of bonds. The energy you need to put in, essentially. Standard conditions, blah, 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 right? So if that means that this has a higher mean bond enthalpy, you need to put more energy into breaking it. So that means this one would be slower, that one would be faster. So that's actually correct. It's B. There you go. Next, which statement about the absorption of radiation is correct? So infrared radiation can result in the breakdown of the ozone layer. It's not infrared, it's ultraviolet. Next, it says ultraviolet radiation can cause some polymers to photodegrade to benefit the environment. That is true. Ultraviolet radiation is linked to global warming. That is not correct. It's infrared radiation, that's heat. And then ultraviolet radiation is used in modern breathalyzers to measure the ethanol in the breath. No, it's not. It's infrared, so that one's out. So it's B. Now, what's the number of sigma bonds in a molecule of methylbenzene? Now, a sigma bond, remember, is just where you have a single bond between two things. So every carbon in an alkane will have 4 sigma bonds because it's bonded to 4 other things. And in benzene, you will have 12 because you've got C6H6. Those C6s, each of them have a single bond between each other, so we have a sigma bond there. And then each of those H's as well, right? So methylbenzene, just give it a quick sketch. 1, 2, 3, 4, 5, 6. There's a CH3 here, right? Fine. So every single bond you have is going to be a sigma bond, right? Every single one of them. So each of these carbons, you've got C6H6 in benzene. So that's 6 between the carbons. So 6 sigma bonds there. And then we've also got 6 between the C and H's as well, so another 6. So that means we've got 12. However, one of them's been swapped out for the CC here. That's fine, that's still the same number. But we have 3 extra ones added here, so 3 more sigma bonds. So that means we've got 12 plus 3, which is 15. So it's going to be D. So it says the skeletal formula of an organic compound is shown below. What functional groups are present? So you should be able to recognize these straight away. Whenever you have C double bond O and H next to each other, you've got an amide link there, an amide. An amine is where you've got C, N, and H's. There's no oxygen. The amide bit comes from the oxygen. Whenever you have a C, O, H, unless it's a carboxylic acid, that is an alcohol. If you have a C double bond O, OH, you have a carboxylic acid. If you can if you have a C double bond O, O, and then a carbon there, that's an ester or ester link. So if you can recognize what these look like in molecules, this question's pretty alright. Because you've got a C double bond O, NH, so that means there's an amide here, and then the C, OH, so that's an alcohol, so it's A. Done. The reason it's not carboxylic acid, no COH. The reason it's not an amine is because it's got CONH, and amine is just CN with H's. And then, as well as that, it's not a ketone because this is a C double bond O, NH next to each other. That makes it an amide. You can't have an amine ketone alcohol. That's not what that is. And there you go. So the structure of a drug is shown below. How many chiral carbon atoms are in this? So if we have a look together then, so you just got to look for everything where you've got 4 different groups. This carbon does not have 4 different groups because there's 3. This one doesn't either. That one doesn't either. This one has a methyl and one there and then one there and one there, so that's 1. And then here, that's got double bond, so that's out. And then we've got what? We've got an F there and then some other alkyl bits there, so that's 2. And then we've got another here, that's all H there, 1, 2, it's not benzene, 3, so that's 1. Then we've got what? C, OH, C this, and then a hydrogen, so there's another 1. And then what else we got? So that's 1, 2, 3, 4 so far. Strong start. And then here, there's an H and an H there, so nope. That's like what? CH3, another one there. That's 1. And then here we've got like that there, and we've got this here, then the hydrogen there, and that's another. And we've got what? HH there, so nope, that's going to be a H, this and this there, and then that. So that is 1 as well. That's an OH. Let's see something else there, and then that there. And it's a double bond O, so nope. That's C bonded to a HH there, so nope. And there you go. So what's that? 1, 2, 3, 4, 8. It's 8. Yeah, there you go. So now, which one has the highest atom economy for making ethene? So remember, atom economy is where basically you've just got your MR of the thing that you need or want over MR everything. So same what I need over the MR of everything, basically. So what I mean by that is with the MR of this over the MR of this. Now, you can just go and calculate it rapid fire through all of these and you'll get it. Just for the sake of time, I'm just going to skip ahead and do that. That's what I would do, so it's B. Next. Complete combustion of this many moles of an alkane produces that much H2O. What's the molecular formula? So we've got this mystery alkane, and you're making H2O, an X number of H2O. And all we know is that we have this many moles of this alkane. So remember that we've been given the mass of this water. So a good start would probably be to work out the moles of the H2O. So if we do that, we'd have 5.0 over 18. 40 over 18 gives us 0.3. So 0.05 moles of this gave us this many moles of that. 0.3 divided by 0.05 is probably going to give us what we need. If we do that, we get 6. That gives us a ratio of 6. Because remember, that's the molar ratio. That's this many gives you 0.3. So that means it's a 1 to 6. So we need to think, which one of these can give us 6 H2O? So that won't, because it's H5, that one, because that won't, and that one, and so it's got to be D. And that's how you do that. So the structure of the painkiller shown below, a tablet contains this many moles. So it's going to be mass equals moles times MR, so we're going to need to work out its MR. So we've got a 12 here and 3 hydrogen, so 12 plus 3. We've got a C double bond, so it's going to be a 12 plus 16, plus then the nitrogen's 14 plus 1, and then we've got 6 carbons in that benzene ring, plus then 1, 2, 3, 4 hydrogens, because the other ones have been swapped, so that's plus 4, and then a plus 16 for the O, and then it's 1 for the H. So the MR is 151. So we do 3.31 times 10 to the minus 3 times your answer, you get 0.4998 grams, which is roughly 0.5 grams, and if we times that by 1,000 to get milligrams, we get C. So this compound's reacted with hydrogen gas to form saturated compounds. So they've told you it reacts with hydrogen gas to form a saturated compound. You need to look at everything in this and see what could react with that. So there's 2 alkene groups. We've got 2 lots of the C double bond C's there, right? Those will react with hydrogen, but there's also this nitrile group here. Nitriles will react with H2s, and it will get you CH2. You'll get an amine from it. So each nitrile group reacts with 2 lots of H2, and each alkene, remember that these only need 1 hydrogen because they will already have got other stuff on it. So they will already have hydrogens and other stuff on it. So that means we're going to need 2 H2s as well here. So therefore, in total, we need 4 H2s to react with this singular thing here. So they're going to be in a 1 to 4 ratio. That means the moles of the H2 is going to be 4 times that. So that's what, 0.05 times 4, which is going to be 0.2 moles. Now they've told you it's at room temperature and pressure and so forth. So that means that the volume, moles equals the volume over 24 decimeters cubed. So the volume is going to be moles times 24, which is 0.2 times 24. If we do that, we get 4.8 decimeters cubed, which is C. It's recognizing that that also will react with hydrogen as well. So it's again remembering in your organic synthetic pathways is just literally think what goes to what, and that's it, right? So these will become alkanes because, you know, there's C double bond C there, C double bond C there. You should be able to recognize off the bat, this is here, this is what it can do. That can react with hydrogen, and it can become an amine. So just think of every single bit one by one and be like, do I know anything where it can react with hydrogen? Now it says butyl propanoate is hydrolyzed by aqueous sodium hydroxide. What is one of the products? So butyl propanoate means, so propanoate means that was propanoic acid originally. So 1, 2, 3, propanoate, O, and then butyl is where the alcohol must have come from. 1, 2, 3, 4. But I don't really care about that. That's what the carboxylic acid derivative was because you can see the ester link here. So if that's the case, when you add aqueous sodium hydroxide, remember that hydrolysis is breaking this down into an alcohol again. That will eventually become like an OH, so you'll get your butanol back, but that will become a carboxylate ion because C double bond O, O minus is a carboxylate ion and Na plus. So it's going to be 3 carbons of that in it, whichever one fits the bill there. So that's C3H7O Na, 1, 2, 3. Oh, there's 1 oxygen, so that's out. And then 10, that fits the bill, so it's B there. This one's 1 oxygen, that's the wrong one, it's 4 carbons in there. So now it says the infrared spectrum of this compound shown below. Which compound could have made this spectrum? So you just got to look at the peaks and start side by side. So the way I like to think of it is that this is your baseline if there's nothing there. So that's your baseline. Any deviation, even as small as like that, could be a peak. So our first peak we see is that there's quite a sharp one at 3,000. So if we look at our data sheet, I have it up on a separate thing. That's probably going to be, so it's what, 3,000 to about 3,100-ish. That could be CHs and the other options. It's not really going to be a carboxylic acid because that's broad. It's not going to be alcohol or phenols because that's like 3,200, 3,600. It's not going to be amines or amides. It's probably just that, to be honest. So that's one of them. And then if you look here, now at like 1,700, we can see that that's a peak there as well. So that's probably what? A C double bond O? Cool. And then what else do we have? All the rest of them are a bit boring. I mean, we could... yeah, there's nothing else really interesting going on there. So if we look at those options, we need to just think whatever can fit these two. So 11, if we have a look... oh no, wait, no, sorry. This could also be a CO single bond as well. So if we look at that, OH, C2OH, alcohols, well, no, it's out the range that we want. C double bond OC, so that's going to be C double bond OC. That fits the bill, and it's going to have CHs, so it could be this. The NH stuff, well, we didn't identify that, and it also fills out the range. That would have a peak in 3,300 and above, so it's not that, and the same reasons for that too, so it's got to be B. So next it says, which one will produce two triplets in the NH-NMR spectrum? So if it's a triplet, what that means is the N+1 row, so you've got the adjacent carbon next to it, is going to have CH2. So you've got to find anything with CH2s in it and see if that fits the bill. So CH3, CH2, that will give you a triplet, and then there's a CH2 here, so it's possibly that. CH3, CH2, and so forth. Let's see, so if we do CH2 here, then C11O, CH2, CH3, it wouldn't give you two triplets because those are in the same environment, and that carbon in the middle doesn't have any hydrogen, so it's not that one. Here, the reason it would is because these are different environments, because you've got CH3 there, CH2, C11O, CH2. That is different to that, so you'll get two separate of them. Here as well, same for the same reasons above, you would get, what's that? So H. That's the same. Oh, so they're the same environment. And then the same thing there, the same environment, so we can get two separate peaks. A, done. Which equation could be the part of the propagation step of this to form this? So when you've got propagation, what that means is radical plus non-radical makes something plus radical. That's what it is. It's always radical, non-radical. Whereas initiation is making the radicals, and then termination is radical, radical, mopping them up. So any one of these is going to go, what? So from this to that. So C5H12 eventually somehow becomes C5H11Cl, right? So it's got to react with a radical. So it could be that this was a radical to this, so some radical form of that, or it could be that it reacts with a Cl radical. So if we look at the options that we have, a C5H11 radical plus Cl2 makes this. That does fit the bill. C5H12 plus a Cl radical. You don't really get H radical on its own. It would be this becomes the radical, so that one's out. C5H11 plus that. To cut around to termination steps, it's D. So which species can act as a nucleophile? So if I say what nucleophile is, everyone says an electron pair donor, but they don't actually have a clue how to represent that, what it means. Don't memorize definitions, use your common sense. If you can donate electrons, right? So if I have like this slightly positive, delta positive carbon, delta negative carbon, it wants to somehow donate its electrons, whatever this thing is, to it. For it to be able to do that, it has to have electrons to donate. So it's got to have a lone pair. If you don't have a lone pair, it ain't going to do it. Loads of people tell me it's got to be the charge and this and that. NH3 isn't charged and it can do it. Cl- is charged and can do it. So it's not the charge that makes it. It's the fact that it wants to go to a carbon that's short of electrons. That's why it's called a nucleophile. Nucleus is positive. Phile means it fancies it. So if it's got electron pairs to donate, it has to have lone pairs. So which one of these can? Well, that's got a lone pair, that's got a lone pair, and that has a lone pair too. So it's all three of them. So it is A. Next it says, which isomers of C5H2O have 4 peaks in its their NMR spectrum? So just a real quick sketch. So 1, 2, 3, 4. So 3-methylbutane-2-ol. So that's what here, and then here. So that's 1, 2, 3, 4, and they're the same environment because obviously CH3 as well. So that's 4. So that one's definitely 1. Next we have 2-methylbutane-2-ol. So 1, 2, 3, 4 because it's butane, and then it's 2-ol. So OH here, and then we have a CH3 here. And an H3C there. So that's 1, that's 1. They're the same environment. There's a 2 there, 3, 4. So that one does. 2-methylbutane-1-ol. So 1, 2, 3, 4. OH here. CH3 here. And that'll be H2. So that's 1, that's 2, that's 3, that's 4. It's only 1 and 2, which is B. So now here's a question about unsaturated hydrocarbons, and it's asking what the systematic name of this hydrocarbon is. So find the longest stem. So 1, 2, 3, 4, 5, 6. So we know there's a hex part in it. And then just name the rest from that. So we know that there's what? 1, 2, 3, 4, 5, 6. So our options are we could go hex 1, 2, 3, 4 ene or 2 ene. So we try and use again the smallest numbers we can. So 1, 2, so it's hex 2 ene. 1, 2, 3, there's a methyl group there, so it is 3-methyl hex 2 ene. So it's systematic. You've got to work it out systematically, bit by bit. Now it says, outline the mechanism for the reaction of hydrocarbon A with bromine, and the structure has been provided, include curly arrows and relevant dipoles. I always think it's useful to just understand what's going on in terms of electron movements. Whenever you're doing a mechanism, you need to think of it as electron pairs, or electrons are going here and here, right? So Br minus, sorry, not Br minus, a Br and a Br, sorry, are chilling. And also you should be able to recognize that if it's Br and Cc, that's going to be electrophilic addition. But even if you didn't, you can work it out. This has got hella electrons in it, so many. Right, so what it does is it actually makes these become polar. Think of it like this. There's a lone pair here. These are electrons. Electrons and electrons repel. These electrons are repelling these, making them essentially get shoved this way towards that like that. right? So now you start to get this slightly positive, this dipole forming here, and then a slight negative here. Now, because this is an electrophile, it wants electrons, it's an electron pair acceptor, it wants to nab them from somewhere. So this place is full of delicious electrons. So what happens is it donates a pair to that bromine. And the way I like to think of it is that now you're adding more electrons here. These are going to repel even harder, so much to the point where they're pretty much nabbed by that bromine. Right? So that means this bond breaks and actually gives the electrons to that bromine. So now as a result, you're left with CH3C, and then like the CH3, CH2, CH2. I've drawn that horribly. Just draw it in the same line, you know what to do. C, a Br, an H there, and then a C, CH3, and an H. This carbon here, though, is missing a bond. That's why it forms that carbocation. It's like, oh no, I'm missing a covalent bond. So then what happens is that remember that this has taken both of the electrons in the pair. Now it has 2 electrons, a lone pair. It's got an extra one than it should. Remember that this is heterolytic fission because both of them are going to 1. So you've got a Br minus here. This Br minus donates its electrons there. So it's actually acting as a nucleophile because it's an electron pair donor. So electrophilic addition actually has, the electrophilic addition part was there. This is actually acting as a nucleophile because it's donating it there. So these electrons given to that, and you end up with the whole thing, blah, blah, blah. I'm too lazy, but then I'm just going to draw the Br and the Br, and that's how you do it like that. So it's just really important when you're learning this or understanding it, just think of it in terms of electron movements and what's happening. That makes it a lot easier. So that's electrophilic addition. Now it says, what is this? So compound B and C is branched hydrocarbons that form structural isomers of those, blah, blah, blah. They're stereoisomers. B has cis and trans. It doesn't have optical isomers. C has optical isomers, but no cis and trans. So what's a structural isomer? So it is the same molecular formula, but different structural formula. All right, and then stereoisomer it's where you've got the same structural formula, but different arrangement of atoms in space. So if you look at like 2 alkenes, like EZ isomers, if you drew them structurally, their structural formula, like the CH2, the this and this and this, blah, 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 CH2, CH2, whatever, right? They will have the same ones, but if you draw them physically, they look different. That's why it's called that. Now it says, draw the cis and trans isomers for the branched hydrocarbon B. So yeah, it's C6H12, right? C6H12 is an alkene. So if it's an alkene, and it's cis-trans isomerism. Cis-trans isomerism is where both of the carbons in the double bond have hydrogen, and then the other things are different. So draw your double bond, because we know it's going to be that, and we know they're going to have 2 hydrogens if it's cis on the same side. And then you just fill in the rest. These two have to have 2 separate groups. So we've got, what, 1, 2, and how many carbons is it? 6. So I'm going to put an H3C here, and then a CH... can I be lazy? You can do that. CH2. That's where they're on the same side. Both these are the hydrogens. So that's where you get the cis isomerism from. So trans is where they're opposite H, and then, you know, what's that? To draw it the other way around. H3C. I'm going to do it like that. It's easier. CH2, like that. So you know that it has to be, well, the only option it can be is that it's got to be a carbon-carbon double bond, or it would be a cyclo something as well. Because you can see it's CnH2n. Can't be the cyclo alkane because that wouldn't give us the isomerism, so it has to be the carbon-carbon double bond here. Right? Now, it says draw the 3D structures for the optical isomers of compound C. So, compound C has told you what? Compound C has optical isomer. Compounds B and C both have them. So they're branched hydrocarbons. Oh, they've also told you it's branched. Sorry, whoops. So here now, if we have optical isomerism, it means that you have to have a chiral carbon in the middle. It's still going to be an alkene of some sort. There's just got to be a chiral carbon. So I usually just, again, start by drawing just the fundamental parts out. I know that there's going to be a carbon, and I've got to draw it 3-dimensionally. So it's going to be the dotted lines and your wedges. And then I know that this is going to be the mirror, like this. And then I put the gaps in. So I've got, what do I have to put in this? I've got to put a C1C in somewhere, and then everything else. And I've used up one of the carbons. So I'm just going to plunk this C1C somewhere. So it would be what? CH2 like this, and then that's going to be CH2, because mirror images, right? And what am I left with? 1, 2, 3, 1, 2, 3. So I'm left with 3 more carbons and hydrogens and all that stuff. So the options are CH3 and CH2. So I'm going to put a CH3 here. The mirror image would be H3C there. And then I've got the CH2 stuff. So it's H5C2, C2. There you go. And there's your optical isomer. Oh, and sorry, whoops, we're left with the hydrogen as well there. So that's your optical isomers there, done and dusted. If I chose to put CH3 there and a CH3, that's not optical isomerism anymore because there's no chiral carbon. The fundamental thing is that there has to be a chiral carbon for 4 different groups. That's why I put the H there. So now it says D and E are 2 more structural isomers of this C6H12. D and E do not show stereoisomerism, and we've got some NMR and infrared spectra for D and E. So indeed, the number of peaks in the proton NMR spectrum is 1. So that means that we all have the same the hydrogen environments, and also the carbon environments are identical as well. And there's no peak at 1620 to 1680. So 1620 to 1680 is C double bond C. So this is something that has no double bonds and only has one carbon environment, and it's C6H12. The only possibility it can be is that it has to be a cycloalkane, because that's anything with CnH2n is either an alkene or a cycloalkane. So in that case, it's just got to be 6 carbons in a cycloalkane. So 1, 2, 3, 4, 5, 6. And all of those are the same hydrogen environment. So that, and that. So they're all the same. That's D. And then if you look at E, well, we know it has a C double bond C, and we know it has one hydrogen environment, and we know it's got 2 carbon environments. So I'm going to start with the obvious, which is there's a C double bond C in the middle. I need to think what I'm left with. So I've got, how many is that left? We've got 4 more carbons. So my options are I could probably put 1, 2, 3, 4 carbons sticking out here with something's going on, CECs. That means we have this carbon environment's 1, but that's the same as the other one there, so that's 2, and then, sorry, 1 as well, sorry. And then we also have these, but they're the same as that, so now that's 2 carbon environments, and we just fill in the hydrogen, CH3, H3, H3C, H3C. And then it says draw the evidence and explain how these will provide evidence for that. So, whoops, I've just said it all verbally. So, for D, H in mass spectrum, oh my god, and carbon 13, 1 peak, all C and H, same in the same environment. And then there's also no C double bond C. And then in E, 2 C environments, because there's 2 peaks. We know that there's a C double bond C there, and also the all H's, same environment, because there's only 1 peak. So my handwriting is abysmal, I'm just trying to be fast. So these are all in the same environment, so there you go, done. So now it says ozonolysis is used in organic synthesis. Ozone breaks down C double bond C to form carbonyl compounds. For example, the complete ozonolysis reaction of 2-methyl-butyrene is shown below. So you can see you've got this butyrene going on here, and we're reacting with ozone, and we've got what's going on here. We've got a ketone, and then we've got another ketone there as well, right? Not ketone, aldehyde, sorry, whoops, oh my god. C double bond OH, so it's an aldehyde, let's say ketone. So it says now, draw the structures of the products you would expect from the ozonolysis of the 2 compounds below. So we would expect it to make an aldehyde and ketone. So in the same sense, you can see that this carbon in the double bond here has got an oxygen there, and then this one's got an oxygen there. So in the same sense, we will have this, wait, what? It's this, that, but now we have a double bond O from that one carbon, and the other carbon from the other side will have a this, and then a double bond O like that. There you go. Again, one of the carbons from the double bond will have a double bond O, so we're going to have this, then a double bond O there, like that, and then here. Let me make that a bit better, sorry, a little longer there. And remember, there's a carbon here from our double bond, I'll draw that stick out there. So it's going to be this as well. It's literally comparing it like for like, using what the questions told you. And you can check that adds up, and it doesn't. Now it says the mechanism for ozonolysis takes place in several steps. The curly arrows in the first step are shown below. In the box, draw the structures of the products of the steps. So this is what I meant by saying you really need to focus on what's happening with the electron movement with this kind of stuff and not panic. Because everyone looks at this like, oh my god, I don't know what this mechanism is, bro, I haven't learned it. That's not how it works. You got to look at it bit by bit and see what's happening. So what's going on here is that this double bond is breaking, and it's giving electrons away there to this oxygen. This oxygen is giving electrons to this carbon and bonding with it. Not the double bond, the carbon. So I know at the very bottom we're going to have C single bond C, and we're going to have H3C, CH3, and RHs. Draw them nice and spread out for yourself, right? Now, if that double bond is giving electrons to that oxygen, it means that this carbon, or that carbon's binding with that oxygen, but we can see that this oxygen's giving its electrons here. So then we definitely know for sure that this carbon's bonded to that oxygen, and this one's bonded to another oxygen there, right? Now, if you look at this one, this oxygen-oxygen double bond, a lone pair, sorry, not a lone pair, and a pair of electrons have been given to this O+, which wants electrons anyway. So that double bond is broken down into a single bond between these two, so it's this and this. So you need to think of it in terms of electron movements, otherwise you're screwed. That's not that hard. Oh, wait, whoops. That's an H3C, sorry. So, there. So now it says, this is the analysis of an unknown compound X, and properties are shown below. So we know its molecular formula is CXHYF60. Fine. We know it has a CF functional group, we know it has a COC functional group. And we know that it's got 1 chiral carbon. So at a pressure of this many pascals at 30 degrees Celsius, this many grams of compound X is a gas with a volume of that. Determine the molar mass and its molecular formula. So if this isn't hinting to you that we're going to use PV equals nRT, yeah, we are. So PV equals nRT. Let's list out what we have. So our pressure is 1.07 times, sorry, what's 1.07 times 10 to the 5 pascals. We know that its temperature is going to be 273 plus the 30, because we need to convert it to Kelvin, so that's going to be 303 kelvins. what do we also look for? So we don't know what n is. N is what we're going to be looking for to find out what this molar mass is, because mass equals moles of it. Sorry, mass equals moles times m, or molecular mass equals mass over moles. R is given to you so in the formula book, so it's 8.314, PV equals nRT, and they've told us that the volume is 186 centimeters cubed, but the problem is we've got to convert that to meters cubed. So that's going to be 186 times 10 to the minus 6. So the way I think of it is that so to go from 1 centimeter to a meter, you're dividing it by 100. From 1 centimeter squared, that's like saying 1 centimeter times a centimeter, so that's going to be, if you're going to a meter squared, you're going to divide it by 100 squared. So then if I'm going from 1 centimeter cubed to a meter cubed, I'm going to divide it by 100 cubed, and that's where that comes from. That's how I do it every time. So then if I rearrange the equation, I get n equals PV over RT, so that's going to equal, so pressure is 1.07, times 10 to the 5 times 186 times 10 to the minus 6 over RT, which is 8.314 times 303. If we do that, you get 7.90 times 10 to the minus 3 moles. Now, again, whenever you do calculations, you need to figure out, what am I actually going to do with this? Why have I worked this out? They've told us that we want to find the molar mass of this, so MR equals mass over moles. That's why we worked it out. Well, that's why I did anyway. So then what we do is we do 1.327, because that's the mass of what we have, over 7.90 times 10 to the minus 3, and we get an MR of 168. Now, the molar mass is 168, but how do we work out its formula? Well, they've told you that there's definitely a CF in there, and we know that there's 6 Fs in there. Well, they've told us that there's a COC in there, and we know that there's 1 oxygen in it. So definitely by that, we can take out the 6 Fs and 1 oxygen. So if we do that, that would be 168 minus 6 lots of what? 19 minus 16. What does that leave us with? So 168 minus 616, that gives us 38. So we know that the remainder of it is carbon and hydrogens, right? And we know that there's COC in it. Okay, so to now work out what's left, all of the stuff that's left is some number of carbons and then some number of hydrogens as well. Okay, cool. So we know that there's a CFs in this. We know that there's 1 chiral carbon as well. And 6 of the... So this would have been full of CHs, but we've replaced 6 of those H's out with an F, and then we've also replaced one of them with a COC. So there's multiple ways around it. What I would do is just muck about until you get what you need. If we do 3 lots of 12, that gives us, what, 36, and there's 2 H's left, so that means the formula should be C3H2F6O. In terms of its structure, they've told you it's a chiral carbon, and they know we know some fundamentals about it. So I'm going to start with our chiral carbon. That's probably the best bet. This chiral carbon has to have different things on it, no matter what. So remember that we have 2 hydrogens to work with. So there's an F here. I'm going to go with that, and then probably an H. It's a chiral carbon, so let's think of what we can put that's different next to it. So I'm going to try and put the oxygen next to it, because we know there's a COC, right? Then this carbon has to have other stuff, something different to the other ones, so you can't have this O on it on the other side, so we're probably gonna have another carbon, and then we have to think of how many hydrogens we have left. If I were to put an hydrogen there, and then like an F and F, if I put an F here, and then an F there, and then an F there, that's 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and we've got 1 hydrogen left there, and that should give us a chiral carbon, because that's got 1, yeah, that's a chiral carbon there. There you go, done. So this question's about carbonyl compounds. Describe a chemical test that can be used to identify a carbonyl group. So a carbonyl group is where you're looking for either anything with a C double bond O in it, which could either be a ketone or it's an aldehyde. It's not asking you how to differentiate them. It's just asking you how to identify the presence of it entirely. So the only way you can do that is by using 2,4-dinitrophenol. So what you do is you add 2,4, then you can write the whole thing. I'm just going to write DNP because I'm lazy. And you would, what do you see? Because remember, you need to describe how you're going to confirm it. So you need to say what you're going to see, right? So you're going to form an orange precipitate. But then it says, how could the product of this can be used to identify the carbonyl compound? So what you can do is you can take this and you can, we can measure the melting point of the precipitate and then compare it to known values. Because if you have like a set value of this precipitate's melting point, then surely it should be the same across the board. It's got impurities in it, then it starts to go funky. So that's what it's looking for, is just remember the question's asking for a carbonyl group, not how to distinguish them. Then it says, describe a chemical test that identify whether a carbonyl is an aldehyde. Well, there you go. That's what they're asking you now, is to differentiate between the two of these. This cannot be oxidized into carboxylic acid. It's stuck that way forever, but this one can. You can oxidize that. So something else gets reduced, so it'd be Tollin's reagent. So remember, that's silver nitrate dissolved in ammonia. What happens is that this gets oxidized, the silver nitrate, the silver gets reduced. So if the silver's reduced, it goes from Ag plus to Ag solid, so you get a silver mirror. That's why that silver-mirror forms. Because remember, when you oxidize something, you have to reduce something else. Students provided with 2 unknown carbonyl compounds are analyzed and have this identical percentage composition by mass. We've got mass spectra here, and then it's saying find out what it is. And rule number 1 of all of this is to collect what you know straight away from the question. All right, every single time. What I mean by that is look and what can you objectively conclude and say, this is what the question has told me. First sentence, it's 2 unknown carbonyl compounds. So they're both definitely going to contain a C double bond O in it, no matter what. All right. It's now told us this. There's nothing else we can really work from, but at least there's that start. Some questions will give you hints like that, and you just completely miss them and then end up doing some other kind of rubbish. Use the whole question. Collect all of what you can objectively say first. First thing we're going to do is, well, they've given us a percentage by masses of all of these, and these all add up to 100 if you calculate that. So if we do that, then we can work out the empirical formula. So that's a pretty good start. So if we work out the empirical formula, we've got C, H, and O. That's going to be 62.07 divided by 12. 10.34 divided by 1, 27.59 over 16. So that gives you 5.1725, 10.34, 0.1724. And if you divide it by the smallest number, then you'll get roughly 3 to 6 to 1. So that means the empirical formula is going to be C3H6O. Fine. Now what we need to do is let's figure out what the MR of that is. So that's 12 lots of 3 plus 6 plus 16. And that gives you 58. So look at the mass spectra and see if they match. You've got the biggest peak here at about 58. 58, and then here it's 58. So that must be in the molecular formula as that as well. So the molecular formula is also this. Fine, right? So now what we need to do is our options are, we need to look at these fragments, what's going on here. So if we look at, for example, the F, we can see that there's what, 26, 27, 28, 29. So we've got a fragment at 29, right? So 29 must mean that something has been peeled off here. So when we're peeling, what happens with this is when you're making fragments, you literally just have the whole thing and bits of it break off. So if I just make this a linear thing, 1, 2, 3, H double bond O, and then what's that? 1, 2, 3, 4, and that. That whole thing is 58. So if I break it apart here and get this and this, what happens if I do that? So if I do 58, take away 2 lots of 12 minus what's that? 1, 2, 3, 4, 5. That gives me 29/28. So that means that a fragment there must have been this. So that's probably what F is. And if you want, you can test the other way around because the other fragment has to be CHO. So that's what? 12 plus 1 plus 16. Is there a fragment 29? So it's also there as well. So F has to probably be that. So it's going to be, what does it want us to do? It doesn't ask us, it's not asking for any specific compound like way to draw it. So it's fine. I was thinking of checking if there's like a skeletal thing. I'm just going to do it skeletally. So that's there. Done. So that's the number one. So the other one's probably going to be some funky branch thing. Just think of the other possibilities of what fragments can come here as well. So we've got this big ass one at what, like 41, 2, 3. So we've got one at 43. What is 58 minus 43 is a difference of 15. So this fragment has 15 in it. So the only thing that could really give you a nice 15 of a fragment is probably CH3+. So we've got some sort of thing where CH3+ is broken off, but it can't be the same linear thing there. So I'm just going to move that across and see what happens. So we've got CH3 here, C, and then like a CH3 there as well, and then we've got a double bond O. Fragments I can break up as a CH3. So if I break up a CH3, what's left is going to be 58 minus, well, the rest of it. So it's going to be 43. So is there a peak at 43? That's that one there, yeah. And then we should have one at 15 there as well. So we peeled off the CH3s there. That's fine. If we do that, then that must mean that that's what G is. Because it can't be this. If we did it any other way, it'd just be the same as that. So there you go. That's how you do it. Everyone hates proton NMR spectrum, and I think the reason is, personally, is because you guys just jump about and try and do a bit of everything and then get confused and don't know what you're doing. Anytime I do an NMR spectrum thing, I do it step by step, because otherwise I'll get confused and forget what I'm doing. Always use what the question has told you first, and then dive into it. So as in, what has the question definitely told me? So here, the organic molecule compound H only has carbon, hydrogen, and oxygen, and it has an MR of that, right? So there's only CHs and O, and it's got an MR of 114. Already, that's all we know. It's told you, though, in the question, it has 2 carbonyl groups and nothing else. Use what the question has told you, please. And then you do the peak stuff. So now we know that the only options are going to be these. So that's what we've been told 100% is going on here, but we've also got some other stuff too. The numbers by the peaks of the relative peak areas, which tells you the numbers or proportion or ratios of hydrogen. We don't know if it's the exact numbers because, for example, carbons can't have 6 hydrogens. So it's probably 2 CH3s. So you're going to remember that as well. The other thing is, don't dive in yet. Use your common sense. We've got 1, 2, 3. 3 overall peaks. So we've got 3 hydrogen environments. Collect all the information you need first. Right, now we can start diving into all of the fun stuff. So whenever you're doing these questions, take it peak by peak and just have a think about what's going on. There's a reason that these are all bold as well, by the way. What people do is they'll look at like an R group and then think, oh, it must be this and that and blah, 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 and stick things together. You've got to realize that this is the carbon that you pick up, if that makes sense. So if you look at that first peak, we've got a peak at 1 ppm and list out its characteristics every time. So we know it's a doublet. So the adjacent carbon has 1 hydrogen. And then we also know that its integration is 6. Therefore, there are 6 H's in this environment. Remember that doesn't mean the carbon has 6 hydrogens. That's not possible. It just means it picks up 6 in that environment. What I mean by that is if we have CH3 here and CH3 here, they're in the same environment. It's picking up the fact that these are in an environment and there's a peak. And the 6 comes from the fact that there are 6 hydrogens in that environment. So if you look at what that is on your datasheet, it's HCr. So it's this H in bold, C, R. Now the reason that's in bold is because it's telling you that this hydrogen and this carbon by proxy is what has been picked up. So we know that its integration is 6, so we can't put 6 hydrogens on here. So what must have been picked up by this is that we have, so then we have a carbon here with a CH3 and then a CH3, right? This hydrogen environment's been picked up in this, and that's the carbon it's attached to. Cool. So the adjacent carbon has 1 hydrogen, and we've got some R group here. So that's a piece of the puzzle that we have so far. Again, we're going to look at its characteristics. We know it's a singlet. So the adjacent carbon has 0 hydrogens. I'm going to write no hydrogens just because I don't want it to look like I'm saying OH. And then as well as that, its integration is 3, so it's got 3 H's, right? So if I look at the data sheet, it's this one here because they've told us that there is no, and nothing else but carbonyl in it. So that means that what's been picked up is it's this carbon with its funky hydrogen. But it's told you it's an integration of 3, so this has to have 3 hydrogens on it. And it's a C double bond O, and then something else. I just told you the adjacent carbon has no hydrogen. That's not adjacent to here, it's the adjacent to this environment, because that's the one it's pointed out. And that adds up. This doesn't have any hydrogens, so we're happy there. Then if we look at the peak at, what's that, 3, I'm going to go just 3, but 2.9, fine, we'll be precise. If we look here, 1, 2, 3, 4, 5, 6, 7, there's 7. Anything that's a deviation from that flat line is a peak. So that means it's a septet. Is that the word? Multiplet. Well, I'm just going to say it's a multiplet. You can say that 7 peaks or 7 whatever is, right? So the adjacent carbon has 6 hydrogens, right? And then the integration is 1. So there's 1 hydrogen. So if you look at what's at the 3 point whatever thing, or 2.9, sorry, can't be that. It can't be that. It's got to be this again. So again, that carbon's been picked up with its hydrogen here. I told you its integration is 1, so that stays as 1. And then it's got a C double bond O, C double bond O and whatnot, right? It's told you the adjacent carbon has 6 hydrogens there. That doesn't, so the adjacent carbon to this has to have 6, but you can't put 6 hydrogens on it. So it must be this, CH3, CH3, this environment, right? So then when you're putting the pieces of the puzzle together, you can see that we've got a C double bond and whatnot, and then we've got like this piece here, and then we've also got this piece here. So what it must mean is that, I'm sorry, and this part there, sorry, whoops. So we put the pieces of the puzzle together. One end of it is going to have this CH3, CH3, C double bond O, right? And then what else do we know about this? We know it's got just CHOs only, and it's got an MR of 14, and it's also got 3 hydrogen environments, and it's got 2 carbonyl groups in it. So that must mean that in this case, we definitely have another carbonyl group on this here, right? And that's that piece there. And then we've probably got maybe a CH3 here as well, like so. Because that piece is probably going to be doing that. Because you can see the CH3, 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 there's a CH there. So if you just can't do this, just get to at least this point where you justify all of that, and then the rest is easy. Like you can just leave it there. There's no point spending 8 years trying to work out what the structure is, when a lot of the time that's just 2 marks. So, and to be honest, in the mark scheme it says here, any structure with the molecular formula C6H10O2 and has 2 carbonyl groups, you could literally have just you know, shat out like some random carbonyl. It would have at least given you 1 mark, and then the extra mark comes to the right thing. So doing it step by step like this gives you all the pieces, then you just have to compare them and remember the overall details. Although it looks like there could be this and this going on here, right? This is probably matching that peak there. Because remember, this is probably like the other side of it, and then we've got C double bond O there, C double bond O there, and it's told you as well that we have 2 carbonyl groups in it, so it has to be that. It's just putting all of it together like that. But doing it step by step means you at least secure all the bag. So now it says this question's about compounds that contain a carboxylic acid functional group, which is COOH, remember? Carboxylic acids react with alkalis, metals and carbonates to form salts. Write the full equation for the following reactions and show the structure of the organic compounds. Show it's propanoic acid with aqueous potassium hydroxide. So if I do propanoic acid, that's 1, 2, 3, double bond O, OH like that. C double bond OH, remember? And we're reacting it with, what did they say? KOH. Okay? So it's told you it's an acid, we're reacting it with a base. A definition of an acid is that it's a proton donor, but everyone loves saying that but doesn't know what it means. If something's a proton donor, it means is it loses an H+, it's giving it away, and a base is something that accepts protons. So what it means is that you're going to have something plus H+, gives you whatever it is. So the acid, for example, HA, is an acid because it can go off to lose H+ and give it like that. Whereas if you have like a base B, it's a base because it can gain that H+ and become BH4. So what that means is that this is an acid, so it's losing an H+, so you're left with O- there, right? And then the other thing is that something has to accept the proton. The K+ is not going to do it, it's the OH- that accepts it to give you H2O, right? But then this is going to make a salt because acid plus base makes salt plus water, so there's going to be a K+ there. Next, it says aqueous methanoic acid with magnesium. So we're going to have some methanoic acid with C double bond O, OH, 1, 2, 3, 4. You're going to have 2 lots of them because these only have 1 proton to give, and it's also it's the same as, like, for example, HCl. It's only 1 acid group, so it's going to need 2 of them because Mg makes Mg2+. And you would have let's see, so 2HC, C double bond O, O-, and then Mg2+, and then H2, like that. Then it says the reaction of the alpha amino acid aspartic acid with an excess of aqueous sodium carbonate. So amino acids, all of them in the entire universe, will have a carbon in the middle. It will have a COO, right? H, carboxyl group, and then an H2N, and it's an amine group there, and then it will have an H at the top, and then its R group, which the R group they've told you is CH2COOH. So we're reacting it with excess Na2CO3. That's a metal carbonate. So an acid and a metal carbonate makes a salt plus water plus carbon dioxide. Now there's a carboxylic acid group there, and there's a carboxylic acid group there. So that means it's going to react with both of those. So the salt is going to be on the other side. I've drawn this really badly. H2N, C, COO-, Na+, H, and then CH2, COO-, Na+. Now you need 2 of them, and that's Na2 there. That's quite happy. And that balances out. And there you go. It's always remembering to recognize that an acid is here and here as well. A lot of people will just jump there and be like, oh, but what? Recognizing an acid is there. So remember, always be able to identify a group by what it looks like. Next, then, it says the structure of 2-hydroxybutanoic acid is shown below. All right, and then it says show the flowchart for the reactions involving this. So if we look at this, we can see we've got 2-hydroxybutanoic acid. So again, look at the functional groups. You've got a carboxylic acid group, and then you've essentially got an alcohol. So whatever reactions a tertiary alcohol can do, this will be able to do, because there's no H. So we look at what it's reacting with. It's C6H5 benzene, COOH. That's an acid. So it's a carboxylic acid. It's going to react with either the alcohol functional group or the carboxylic acid functional group. Now, carboxylic acid and carboxylic acid don't react. However, carboxylic acid and alcohol do, because if you do it with acid, you can make an ester. So what you end up with is you've got an ester. So you draw your CH3, CH2, your C, and then your C double bond COOH here stays the same because that's not reacting with the acid, and that's there. But the alcohol group, remember that this is going to become the O and then your C double bond O and so forth. So you get a CO here and then C and then double bond O and then your, the rest of it. So the C6H5 there, like that. So you're making an ester there. It's being able to recognize the groups, because if you see a group, it will do the thing. So if you've got an alkene group, it will probably do all the things an alkene will do. That's how the mentality should be. Now, if we have a look at, for example, here, CH3, CH2, OH, and then H, and so forth, we've got a CN here. Now, what's happening is we've got what? We can see that we've got CH3, CH2, and so forth, and it's become an acid. So we've got a nitrile becoming a carboxylic acid. So you need to think, what reactions can I do, or reagents can I use for that? So if you look here, we've got OH and a nitrile, so it's a hydroxynitrile. So hydroxynitriles you can convert to carboxylic acids, if you remember your synthetic pathways. How do you do that? You use H2O and an acid catalyst. So you're going to use H2O and some sort of H+, and you're going to heat it as well, and that'll get you to the point we want there. Next, what we're doing is you've got CH3, CH2, OH, and whatever, right? And what we're reacting this with? So CH3, CHOH, and H2SO4, and we're refluxing it. So if you just quickly sketch what that looks like. So CH3 is there, CH3 is there, and there's an H, and then OH. So that's the one. Let's just check that. Sorry, C. Yep, so that's another alcohol, right? So we've got an alcohol group here. Alcohol's not going to react with an alcohol, but it's going to react with the carboxylic acid. So again, using acids, so we're actually making ester again. This time it's on the other carbons. It's going to be CH3, CH2, C. That's going to be H. That OH won't react because alcohol doesn't react with alcohol. This is going to become C double bond O, O, and then the rest of it. So C, H, and then CH3, CH3 like that. So being able to recognize the groups, and again, doing that. Now if we look here, we're using NABH4 and we end up with this. So we need to think what we use NABH for. So NABH4 is for reduction, and we can reduce, well, you need to think, what can we reduce that would lead to these? Nothing reduces to make a carboxylic acid. The only routes to making carboxylic acid is by further oxidation. You can't undo that. So, however, you can get back to an alcohol by reducing something. If you're reducing something, you're adding H's into it as well. So if we're taking the H's out, it's going to be a ketone here. So we've got CH3, CH2, so oops, C double bond O, COOH, and there you go. So this question's about polymers derived from carboxylic acid monomers. So polypent-3-enoic acid is an addition polymer. Draw the structure of pent-3-enoic acid and then 2 repeat units. So if we do pent-3-enoic acid, that's what? So it's going to be 1, 2, 3, 4, 5. So it's pent-3-enoic, so 1, 2, 3 there. And the oic acid has got to be on the end because it wouldn't really say one oic acid if that makes sense. So 1, 2, 3. So I'm going to put my oic acid here. So C double bond O, O, H like that. And then I just put the hydrogens in. So that's 1, 2, 3, 4. 1, 2, 3, 4, 4, and like that. There you go. So if I draw 2 repeat units of this, you open up the double bond and everything on either side comes to piece like that. So C, C, H, H, and then what's that? So on one side, I'm going to try and, so that's going to be the outer part. So I'm going to put that there, H3C, that bond's open up. And then on this side, we have all the rest of it. So what's that? CH2, COH, CH2, COOH. And then it bonds with the next one next to it. So it's going to be H, CH3C, C, CH2, COOH. That's open. There you go. Done. That's 2 units done. So now it says butane dicarboxylic acid and 1,4-dihydroxy-2-methyl-benzene react to form a condensation polymer. What is the repeat unit of this? So just, you've got to be like absolutely like silly if you're not just sketching this real quick. 1, 2, 3, 4. Butane, dicarboxylic acid, COOH. Sorry, not COH. That's going to be your COH, sorry. And that's going to be your COH, right? That's one of them. And then it's told you 1,4-dihydroxy-2-methylbenzene. So here's your benzene. 1 hydroxy, 2, 3. So 1, 2, 3, 4 hydroxy. And then 1, 2 methyl. That's what they look like. So when you're doing a condensation polymerization, it's just the same as making esters. The ester links are just coming from here. So this loses an H. The OH is gone there. So what you end up with is just this, where you've got these joined together. Remember that all ester links, every ester in the world has C double O, C, like that. So if you've got that in it, you're in. So it's only asking for 1 repeat unit. So if we think about what's going on here on this end, we're going to lose 1 hydrogen. So that's going to become, so that means we're going to have, that's going to lose its H. So we're going to have C double bond O, and then an O there, and that's open. Then C, H2, C, H2, and then we've got our C double bond O, and then the O, and then it bonds to the rest of this, so our benzene. But now it's on its side, and then that is going to be left open because that's going to bond with that O there, remember. So I'm not going to put an O there because that's implying it's an O with an O. You can also just do this as well, so it's like that and the O's on the other side. Either's fine. There's our benzene, and then what's that? 2 methyl, so the methyl would here. Either's fine. You can go there or there. Now it says 3 repeat units of a condensation polymer as shown below. Draw the structure of the monomer that made this. So if we look, there's a CO bond there. So this must have come from an OH part, from the original thing. Here, we've got a C double bond O and an O here. So that must have been the carboxylic acid originally. C double bond O, double bond O here as well. So that must have been the carboxylic acid. So there you go. And then the rest repeats like the same. So one of the monomers must have been this, HO, and then this. Oh, sorry, now I'm doing skeletal, whoops. Make the bends a bit more obvious. OH, double bond O, and then there, double bond O, OH. Like that, there you go. What is the relative molecular mass of this polymer? So based on that alone, it's going to be this, OH, OH. Because we're recognizing the ester link, that double bond O part comes from the acid. That's what it is. There, there, OH, OH, double bond O, double bond O. There you go. Now it says a polymer is made from 400 molecules of 2-aminopropanoic acid. Draw 1 repeat unit. So it's 2-aminopropanoic acid. So 1, 2, 3. Oic acid means that this would have had a double bond O and OH, but remember that's now open, so there you go. And then on the other side, it's 2-aminopropanoic acid. So amino, 1, 2 amino, N. It would have been NH2, but it's lost an H, like so. That's fine, but I'm just going to make this look a bit prettier by putting that CH3 down there instead, because that'd be an H there. So I'm just going to make this look a bit tidier, because you kind of want to draw them side by side. So again, it's 1, 2, 3, right? But I'm going to just move that carbon down here, just so that it's got either end, if that makes sense. You kind of want to write it like that, because then it's a lot easier. So there's a CH3 there. That's going to be your O there, and then your double bond O, and then your NH there, like that. That's 1 repeat unit. And it says, what's the molecular mass of this polymer? Okay, so we need to think about this logically. So we've got 2-aminopropanoic acid. So the monomers, like, you know, MR is going to be, if you work that out, when you do the MR of it all, it's 89. We have 400 lots of 89 in this. Okay? But each one of them, remember, puts out an H2O, because it's a condensation polymerization reaction. So if you react 2 of them, so 2 react, you get 1 H2O out. So what that means is, because we're doing, if we're thinking about it, we've got 400 in total, that means we will have done 399 condensation reactions. Alright, because that first one isn't condensing with itself at all. So that means we have to subtract 399 waters out, which is 18. So if we do that, we would get 400 lots of 89 minus 39918, which gives us 28418. And that's how you do it, like that. So a student intends to make compound I. Here we go. So we've got what's going on here. So we've got C double bond O, OC, so that's an ester group, and we've got an amine there as well. It says plan a synthesis to prepare 9.6336 grams of this, starting from 2-chloropropanoic acid, CH3, CH, blah, 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 whatever. The overall percentage yield of this is that. So in your equation, include a starting mass of 2-chloropropanoic acid reagents, or whatever. So it's told you in the question, again, with all of these, what can you objectively conclude from this question? What's the question told you? And you're like, 100% this is happening no matter what. Don't go into it and think, oh, I think it's telling me to do this. Look at it. So it's telling you that you're starting with CH3, CH, Cl, C double bond O, OH, right? And we're eventually going to be making this compound I. It's told you that we want to make 9.36 grams. And we're starting with whatever this is, but they've told you that the actual percentage yield of I is 64%. So that's the amount we would like to make. In reality, it might not be that. So now we need to think about what reactions are happening with this. We need to compare this versus this. So if we look carbon by carbon, we can see that there's a CH3 here, and then a C and an NH2, right? So in that case, we're going to have a CH3, a CH, sorry, there's an H there as well. This Cl has to have swapped with an NH2. So if I do it, so that means that this Cl has been swapped with NH2. Fine. If you look at this next part, so we've got C double bond O, OH, we've got C double bond O, O, but then we've got this other bit next to it as well. So what's happened here is we've stuck on a CHH and then a CH3. Like I said before, if you recognize every single link in the world, like what these look like, that's an amine, that's an ester link there, C double bond O, OC. So this must mean we must have used an alcohol there as well. So in order to actually make this thing, we're going to have to do nucleophilic substitution first with NH2. So we're going to swap the Cl with an NH2. So what we do is we're going to make that synthesis, so the reaction. So we need to think about synthetic pathways. So what we will do is we will react the 2-chloro blah 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 with ethanolic ammonia. What that means is you're dissolving it in ethanol instead of water. Now the reason we do that, I mean, I think anyway, it makes more sense, is water has OH minuses in it, and that can substitute there and you get an alcohol. So in order to stop that happening, to make sure you're only getting NH2s, that's why we use the ethanolic ammonia. And what happens is you get nucleophilic substitution, and then that produces the whole thing again, basically, but just with that NH2 instead. So you would have CH3, CHNH2, COOH. Right. Now, as well as that, we don't want any further substitutions to happen, so we need to talk about conditions and reagents and stuff like that, so we need to make sure it is excess as well. Reagents, what you're putting into it, what you're reacting together. Conditions is what the conditions are. So in that case, those are the conditions. So you're going to have excess of this ammonia. That's the reagent. And that's the conditions is going to be that it's dissolved in ethanol. So if we do that, that's nucleophilic substitution. And then the reaction for this would be, CH3CHCl COOH plus NH3 makes CH3CHNH2COOH, right? But this Cl needs to go somewhere. That NH2 swap there, we're going to make Cl minus. One of the Cl minus is actually reacts with another ammonium. So ammonia, sorry. So you actually get this NH4 Cl, and you can see that that fits the excess part as well. So next what we need to do is we need to talk about the next step. So what we're doing is we're esterificationing this. So what we're going to do is we're going to do an esterification reaction. So what you're going to do is you're going to react this. I'm just going to write that product because I'm lazy, but you write the whole thing. Ways, and then we need to think what this is. 1, 2, it's going to be an alcohol with 2 carbons, so ethanol. And you're going to use an H2SO4 catalyst, and you're going to reflux as well, and that's going to be esterification, and it's a condensation reaction. So when we do that, we end up with going from CH3CHNH2COOH plus what's that? CH3CH2OH gives you compound I, which is what we want. So that's going to be CH3CHNH2COOCH 2CH3 plus, and then an H2O shot out. There you go. So that's how you need to do. You need to look at the groups and think of what's happening, compare them side by side. Now, if we do all of that, we need to now think, if we're going to do all this calculating stuff, we need to think how they're going to react in molar ratios. So eventually, this is 1 mole of this is going to go on to make 1 mole of this. And we can see from our equations that 1 mole of this is going to make 1 mole of this. So in our overall reaction from here to I, it is a 1-to-1 ratio, which is a good thing, because that means we can now work out all of the other bits and bobs. We want to make, so if we look at I, we want to make 9.36 grams. Therefore, the moles of what ideally should be used, we'd get would be the same as that because they're 1-to-1. So the moles of I, in this case, is going to be 9.36 divided by its MR as well. So the MR of I is 117, and that gives you 0.08 moles. And this is to make the perfect amount of that, right? So then, if we go back to the start, sorry, I've done the arrow from the wrong way. I meant to say here. So if we go back to our start product, that means the moles of the 2-chloro blah 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 is going to be in a 1-to-1 ratio. It's also going to be 0.08. Remember, that's how much we need to get this beautiful, perfect reaction happening. Okay, so we now know the moles of the 2-chloro thingamabob is this. However, they've told us the percentage yield. So 0.08 moles of this makes, 64% of what the actual amount, right? So the actual amount would be, so 0.08 equals 0.64 times whatever the actual thing is. The actual amount that we want to make is 64% of the original. So in that case, we'll have to use extra of this to get to that. So it'd be 0.08 divided by 0.64 as a percentage. 0.08 divided by 0.64 equals 0.125 moles instead, actually. Therefore, the since mass equals moles times MR, you would do 0.125 times the MR of the 2-chloro whatever it is, which is 108.5, and that gives you 36.56 roughly. Sorry, 0.5625, which is roughly 13.6 grams. This question is about the chemistry of aromatic compounds. J, K, and L are shown as below, and their structural isomers. So again, it's always helpful to just quickly identify what you see here. So we've got an alcohol there, we've got a phenol, and then we have another phenol here. What chemical test can be used to confirm the presence of the phenol group in K and L? So the one that you could do, and the one that I've always learned, is add bromine water, and you get a white precipitate. With carbon-13 NMR spectra, I'm not going to dive straight into looking at the shifts and all of that kind of stuff. I think a very easy thing you can always do is just look at the number of peaks in the carbon environments you have. So and that's what I always do in proton NMR spectrum as well, same thing. I always look at the number of peaks. So with J, it's got 1, 2, 3, 4, 5, 6 peaks. So it'd have 6 carbon environments because of 6 carbon environments. I'm going to write that for short. Then we have 1, these are the same, 2, 3, 3, 4, 5, 5. So then K has 5 for the same reasons. So we've got 1 here, we've got 2 there, we've got 3 here, that's not the same as that. So 4, 5, 6, 7, 8. So L has 8 peaks because it has 8 environments. There you go. So now compound J's are substituted at the 2, 4 positions by chlorine in the presence of a catalyst. Outline the mechanism for the 4 substitution of J in chlorine with the catalyst. So they've told you that we have a 4 substitution of compound J. So there's your 1, 2, 3, 4. So we're substituting on here. Now we need to think what's going to go in and substitute that. It's told you it's chlorine. So it's something substitution. That's the mechanism. We need to think, why is chlorine attacking the benzene ring? The benzene ring is rich in electrons. So it's something that wants to go for something with a lot of electrons. It wants to accept the pair of electrons, so it's electrophilic substitution for that exact reason. So what we do first is we need to initiate. So we need to do some first steps. So initiation is we need to actually generate an electrophile. So what you do is you'd react Cl2 with an halogen carrier catalyst. So for example, AlCl3. What happens is that becomes AlCl4 minus plus the Cl plus. And these charges add up to 0 and there's no charge there. So that's great. This is your electrophile. Then what you've got to do is you've got to show the actual bonds being made and stuff like that. So we've got our benzene here. We have our CH2, CH2, OH here. And this chlorine, Cl plus, wants to bond to this carbon. So the electrons are coming from the ring. So you need to draw a curly arrow like that with with it coming from that ring, because that's where the electrons are coming from. Okay, cool. Then we make an intermediate. So we'll draw a nice little benzene here. We've got our CH2, CH2, OH. Now this chlorine has bonded on here because it's nabbed some electrons from that ring. But the problem is now this ring is short of electrons, so it's positive like that. So the only way to fix this problem is to give electrons back into here. So what happens is this bond breaks from the hydrogen. It gets booted off and substituted. So then what you're left with is a nice, lovely benzene ring reformed. The Cl is now here instead, a CH2, CH2, OH, plus an H, and the Cl, another Cl from the other one there, Cl minus, which gives you HCl. And you regenerate your catalyst as well. The AlCl3 comes back. So that's that step. But the catalyst is regenerated because of H plus AlCl4 minus goes to HCl plus AlCl3. And that's where that extra HCl comes from. And there you go, that's how you do this mechanism. So now it says K and L react with chlorine much more readily than J. Explain why. So if you look at K and L are phenols, whereas J is not. So first step is we've got something to do with phenols. Now we need to think about what's happening when it's quote-unquote reacting with chlorine. When it's reacting with chlorine, the chlorine is accepting electrons from the benzene ring. So if it's doing that, whenever you see questions about reactions, like this is more reactive, less reactive, think about what's actually happening in the reaction. You can kind of figure out where it's going. So this chlorine's accepting electrons from the benzene ring. If it's reacting more readily, it means that this benzene ring must be giving the electrons more readily. So we need to think about why. So in phenols, this might give you a cue to be like, oh, I know why, because of this. So in phenols, the oxygen has a lone pair of electrons. These are partially delocalized into the ring or pi system. Either one's fine. So that means this increases the electron density, which means it attracts electrophiles more strongly. So you can use the question to figure out where to take things sometimes. Next it says compound J, C6H5, CH2, or whatever, blah, 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 is reacted with acidified potassium dichromate, and it makes this product M. Use O to show this. So this is why I said it's really important to recognize organic groups, because if you can see, that is literally just CH2, CH2, whatever, OH. It is simply just a primary alcohol. So if it's a primary alcohol, it can go into an aldehyde and it can form a ketone. But it's told you here, we're doing it under reflux, so we're going to be going straight to the carboxylic acid. So you start with here, like this, and I'm going to do it skeletally just because it's easier. CH2OH. We're adding 2 O's because we're doing both of them. We're making the carboxylic acid. So we're skipping going to an aldehyde, and you would get this COOH and H2O. One way that I personally remember that this is a 2O is because you've got 1 oxygen here, but now we've got 3, so I need to add 2 extra O's to meet that. Now it says a 2-stage synthesis of an amine from compound J is shown below. Fill in the equation for the reduction stage of this synthesis. So let's have a look what's going on here. So we're going from just this, and then all of a sudden we have an NO2, right? So The only difference is that NO2. So what it must be is that we've added the NO2, and the only way to do that is by using HNO3, which is nitric acid, and H2SO4 to generate the electrophile. So it's nitration of benzene. Then you've got that NO2 and it becomes NH2. So we're adding H's to it. So we're reducing it. So the conditions there are tin and HCl. That's one of them. Next, it says fill in the equation for the reduction stage of this synthesis. So when we're oxidizing, we tend to use O's. When we're reducing, we're going to be doing the opposite, which is adding H's. So we're going from NO2 to NH2. So you can see off the bat that we have what? NO2, so that's what? 2 H's on there. Fine. Now you can see the CH2, CH2, OH, CH2, CH2, OH, fine. But these oxygens need to go somewhere, and it's probably going to go into water if we're adding H's. So we're going to have, what, 2 H2Os if we've got 2 oxygens on that side. So that's 2 H2, that's 4 H's. So 2 plus 4, 6 H's. That's kind of how I figure it out, rather than just memorizing it. But sorry, there's an H there. Now it says, 1-phenyl ethanol is a naturally occurring compound in many vegetables and flowers. It can be synthesized to form 2-phenyl ethanol in 2 stages. So we got 1-phenyl ethanol chilling here. And then all of a sudden you get some weird intermediate, and then you do it again, and now for some reason you got an OH here rather than there. So it says suggests reagents, conditions, and equations for each stage of synthesis, and show structures for the organic compounds. Fine. So we need to make some weird thing where we can go from a secondary alcohol back down to something else, and then back to an OH. So you need to think in your head, what reactions can alcohols do? You can oxidize them, that will only take us down the aldehyde or ketone route, so that's not useful. Or we can dehydrate them, because if we dehydrate them, we can go back to an alkene instead. That's the only really other option we can do. So if you guys remember, if you guys have seen that big synthetic pathway OCR's made where you got alkene and it's like this and this and this, you should be able to replicate that and know what these groups look like. So what I'm going to go with is going to probably be the other one. So we're going to dehydrate this. So if we dehydrate that, our reagent's going to be H2SO4, right? And our equation is going to be, well, you start with the original thing. I'm going to do skeletal like this, OH. And then we're dehydrating it into an alkene. So what happens is we're left with this. The OH is gone, but an H is also nabbed from here to make that double bond. So you've got H2O here. Then we're going from an alkene to an alcohol again. So we're just going to hydrate it again. Obviously, you would get 2 products, but it's, that's the whole point, is that the hydration of this alkene can either make this or this. And that's the only way to get back there. So what I'm going to do is I'm going to either use steam or you could say H2O gas. And you need some sort of acid like H3PO4 or H2SO4. And so what you do is you take the alkene that you just made, you hydrate it, and then you make the product that you want. That's literally the only way you can get around that. Like, there's no other way I can think of getting there. So it's kind of just thinking about those synthetic pathways and what routes are possible to get here. Any other route would have just taken you down carboxylic acid, aldehyde, or ketone routes, so it wouldn't help. So now it says, acid anhydrides react in a similar way to acyl chlorides with phenols. Benzoic anhydride is the acid anhydride of benzoic acid, C6H5COOH. So benzoic anhydride reacts with butan 2-ol to form an ester. Suggest an equation for this reaction and show the structures of the organic compounds. UC6H5 4 phenyl groups. So acid anhydrides is where you have a carboxylic acid repeated with itself, but they're bonded together, so you got 2 of them. So C6H5, C double bond O, and then it would be normally OH, but what happens is one of the H's is gone, and then you just have the same thing underneath it here, like that. So that's your benzoic anhydride. So now I'm going to react butan 2-ol, so 1, 2, 3, 4, there's an OH here, and then there's an all these H's here. Right. And it's told you in the question that it makes an ester. So one of these is going to become the ester. Because remember, every ester looks like this. C double bond O, O, C. This came from the carboxylic acid. The H just disappeared. So this other part must have been from the alcohol. And that makes sense, because if you have C, O, and H, these disappear. And only the H from the carboxylic acid is gone. So in this case, we have a carboxylic acid derivative and the alcohol part here. So what we end up with is we have C6H5 and then C double bond O, O, C, CH3, C, like so. But we need to figure out what the other product is. So we've dealt with all of this. That's all gone. What we're left with is there's an H that's been shot off and this whole thing. So the other product you make is C6H5, COH, C double bond O. So we actually make a benzoic acid. So when you're making things with acid anhydrides, they do, yes, react similarly to acyl chlorides, which always look like this. The only difference is acyl chlorides always make HCl. Acid anhydrides will just make the other carboxylic acid. It'll split it back out into two. So now it says carbon-carbon bond formation is used in synthesis to increase the length of a carbon chain. Describe the formation of carbon-carbon bonds in aliphatic compounds by two different mechanisms, and you should include the mechanisms for each aliphatic compound. So the only routes that I can think of are the only thing that we can use to extend the carbon change in its aliphatic, so we're not dealing with things like benzene, is going to be through the use of CN-, which is all to do with nitriles. So you should be which is all to do with nitriles. So you should be thinking about possible ways of doing things with nitriles. So one of the things nitriles can do is it can act as a nucleophile. So because it has that lone pair, it can act as a nucleophile. Electron pair donor, it can give it away. So one of the things it can do is nucleophilic substitution. So how does that work? So you could use a haloalkane plus, and it says reagents as well. Does it say reagents? No, it doesn't actually, but I'd always add it anyway. So with reagents, what that means is what are you going to put in? So you can't just have CN- on its own, you have to put something with it. So I'm going to put KCN in. That will dissolve and give me my CN minuses, which will do the job. So then I'd also dissolve in ethanol as well. Dissolved in ethanol. The reason is because H2O can provide OH minuses, and that would substitute as well, and that'd give us an alcohol. We don't really want that. That's why we want KCN only. So if I chose any one in the universe, I'm just going to say RCHH, and like, I don't know, Cl, for example. Here's my haloalkane. That's my nucleophile, CN-. Now, because this is more electronegative, the electrons are sort of like pushed here. It's like dragged towards itself. So that becomes slightly negative, that becomes slightly positive. This carbon is short of electrons. So this CN- is a nucleophile. So it wants to give away its electron pairs to something that's short of electrons. So it comes here and it's like, yo, I'm going to form a bond with you there. So it does that. The problem is now carbon has 1, 2, 3, 4, and now 5 bonds. There's a problem. So what happens is it's got to boot something off. The reason it doesn't boot these off is because these, I mean, I don't know if this is technically true, but it's how I make sense of it. These electrons are so already close here. Those electrons coming in is just going to give it that final push. So this bond breaks and you get that broken off. So then you get that substitution of R, C, CN, HH plus plus MCl-. And there you go. So that's the first one. Now, the other thing you can do with it is you can do nucleophilic addition. So you can use either an aldehyde or a ketone. And what happens is you will then end up making a hydroxy nitrile. So if I just pick like, oh wait, whoops, and the reagents as well would be KCN, and you need to make sure it's acidified as well. It needs to be H+. So for example, you could use like H2SO4 or something. Now, the mechanism itself, if I choose like any aldehyde in the world, if I just did this and that, again, similar shtick. Try and just forget about like memorizing mechanisms, just think logically what's going to happen. This is a nucleophile. It wants to give away its electron pairs. So it wants to bond to something. Why is it going for this carbon? Well, this carbon must be slightly positive and that must be slightly negative because the electron pairs or have been drawn to this oxygen. So what happens is this bond's here. Now carbon's like, yo, I got too many bonds, bro. I got 1, 2, 3, 4, 5. So I need to boot something off. It's not going to boot this off. It's not going to boot this off. These electrons are already so close to here. You might as well consider this to break. So this double bond breaks like that. If that double bond breaks, that becomes a single bond. So R, C, O, H. This is now stuck on because we've just bonded it like that. But this oxygen, remember, has that covalent bond and the electrons have now gone to itself. Remember that a covalent bond is a shared pair of electrons between two things. Originally, it was one electron. The other double bond was one electron from the oxygen, one from the carbon, but now both of them gone to this oxygen. So now it has a lone pair and it's negative like that. So then we need to figure out how to fix this. That's why we add the H+, the acid, because an H+ comes along and forms a bond with it. So you need to make sure you draw the arrows right. If it's going to bond with the OH, the H+ is going to take those electrons like that. So then what you end up with is you end up with R, C, OH, H, and then the CN there. And that's how you do this. Done and dusted.